In this video, we're going to be going through the sample assessment paper for Unit 2 for the Edexcel IAS Chemistry course, and we're going to be looking at the multiple choice, which is 20 marks out of the total of 80. So if we start off by looking at question 1, this is to do with intermolecular forces, and we want to know which alkane has the highest boiling temperature. So because they are alkanes, of course, they don't have any permanent dipoles and we don't have any hydrogen bonds, so this must all be down to London forces. And what we need to remember is the more points of contact, the better the London forces are going to be. So anything that has got branching, like these two, are going to be further apart. So for example, if you have 2,2-dimethyl propane, you're going to have a molecule that looks like that. And when they pack together, they don't pack particularly close. If we compare that to 2-methyl-butane, again, they don't pack particularly close. When we get to butane and pentane, these can pack right next to each other. So we can get the butane like that, and the pentane like that. And what we can see is the butane is shorter than the pentane, so it has less points of contact. Therefore, our highest boiling temperature is the largest amount of London forces, the biggest amount of packing, or the more points of contact in your packing, as well as the highest molecular mass. So our answer is going to be D, pentane. For question 2, again, looking at intermolecular forces and their linked boiling points. However, this time we've got OH groups, so we're starting to think about our hydrogen bonding. Remember, anything that can make an OH group is going to be able to make hydrogen bonds. And the more OH groups we have, the stronger or the more hydrogen bonds. So when we look at our 4 substances, we can see we've got 3 OH groups in W, 1 in X, 0 in Y, and 2 in Z. So in terms of increasing boiling points, going from the smallest up to the largest, we're going to go from 0, 1, 2, 3. Therefore, we must be looking at Y first, followed by X, then Z, and then W. And that is going to give us B as an answer. For part 3, or question 3, again, we're still looking at our hydrogen bonding and intermolecular forces, and we want to explain which of these is not explained by hydrogen bonding. So the fact that group 1 hydroxides are soluble in water is not actually linked to hydrogen bonding, so in reality our answer here is A. But let's look through the others just to double check. So for B, the fact that many alcohols are soluble in water, well, that must be due to hydrogen bonding because you have your OH groups forming H bonds or hydrogen bonds with the water. So we have an interaction from our hydroxyl group. The density of ice being less than the density of water, well, that's again due to the hydrogen bonds holding the water molecules in this ring structure, which creates these open spaces, meaning they pack less, so it has a lower density. And with the melting temperature of water being abnormally high for a substance being that small, again, this is to do with the fact that we have got these OH bonds forming the hydrogen bonds in between each of the different molecules. So our only answer that we can have here is A, the group 1 hydroxides being soluble in water. Question 4 is looking at hydrolysis. Which of the compounds are hydrolyzed most rapidly? Well, we need to think about the 2 different patterns that we have. So going from the fastest to the slowest, there are 2 different things. We can be looking at the halogen, so we have the iodo, followed by the bromo, followed by the chloro, which is the slowest, and this is all to do with the bond strength because we get increase in bond strength, which means the chloro bond, the carbon-chlorine bond is much stronger, therefore more difficult to break. But we must also think about the structure, and we can have tertiary being the quickest, followed by secondary, followed by primary. So when we take both of those two things together, we can see they're all chloro, so it's going to be related to our structures. So if we have one chlorobutane and one chloropropane, both of these are primary structures. So they're going to be the slowest. So that leaves us with C and D. And 2-chlorobutane is a secondary, whereas 2-chloro-2-methylpropane is a tertiary structure. Therefore, that is going to be our fastest. Question 5 is looking at the systematic name for this particular molecule. And we can see that we've got some information here that we know we've got double bonds, we've got bromines, and they're telling us that these are all E substances. So we have to just figure out where we've got our carbons and what is our chain. So our longest continuous chain is going to start at the double bond, which is carbons number 1 and 2, and it's going to continue along the centre, which is then 3 and 4. So that can get rid of but-2-ene, and it can also get rid of the pent-2-ene, because we know that this is going to have a base structure of but-1-ene. Then we have to look at where we have our substances being attached. So we have a bromo attached to carbon number 1, and remember this is a methyl group that's attached to carbon number 2. Therefore, we're going to have the 1-bromo 2-methyl, and we know that it's but-2-ene, and we know that it is the E isomer because all of our answers are E isomers. So we just have to figure out, is it B or D, which are both the 1-bromo and 2-methyl, but we have to remember that they should go in alphabetical order for our chains. Therefore, the bromo comes first, so our answer has to be 1-bromo 2-methyl but-1-ene. Moving on to question number 6, we're looking at the 1-bromobutane reacting with alkali in this reaction, and what is the type of reaction and mechanism. Well, we have to look here at what's actually happening. So first of all, we have this OH minus, and anything that is a negative charge is going to be a nucleophile, meaning it is negative itself and is attracted to an area of high electron density. So that can automatically get rid of A and B. And then we have to look, are we adding or are we substituting? And you can see here that we're actually swapping the places of the Br and the OH to make the alcohol and the bromine. Therefore, because these swap, that must mean that this is a substitution reaction. We only get addition reactions when we have double bonds, and there are no double bonds here. Therefore, our answer must be D. For question 7, which of the following compounds could be oxidized to a carboxylic acid by refluxing with potassium dichromate and the sulfuric acid? Well, in order to make a carboxylic acid, we must have a primary alcohol. So this is essentially just another way of asking which one of these is a primary alcohol. So if we look at A is a secondary alcohol because this OH is attached to a carbon with only one hydrogen. So this is a secondary alcohol. Here, the OH group for B is attached to a carbon that is attached to all alkyls. Therefore, this is a tertiary. For C, very similar structure to A, where the carbon is attached, the OH is attached to a carbon with only one other hydrogen, which is secondary. Therefore, our answer is going to have to be D, but we can double check. Here's our OH group attached to a CH2. Therefore, that is the primary, and our answer is again D. Question 8 is now looking at topic 8, our redox and our inorganic chemistry. So which of the following statements about trends going down group 2 is correct? So A and B are very similar, talking about the thermostability of the nitrates and carbonates, each saying that they decrease. Now, both of these are wrong because we actually see an increase in thermostability because we have a bigger cation, which means we get less polarization. And remember, in order to get thermal decomposition, you need to have polarization of your anion by your cation. So when we have this less polarization, in reality, these are more stable. Now we have to look at the C and D, which is solubility, and hopefully you remember that for D, the solubility of the sulfates, we know that the test for sulfate is when we make barium sulfate. So the formation of that precipitate is the test for your sulfates. So as we go down the group, barium is near the bottom of the group. That must mean that these are more insoluble. So our solubility is going to decrease because they are becoming more insoluble. Therefore, our hydroxides must be the correct answer. And we know this because at the top, with magnesium hydroxide, that is a precipitate, whereas barium hydroxide is not. Question 9 is a chemical test question, again linking into our Topic 8, our redox and inorganics. We've got colourless solid Q was warmed with sodium hydroxide and a gas was evolved that turned damp red litmus paper blue. What is Q? Well, the key thing is this damp red litmus paper going blue. That is telling us that the gas is ammonia, and that can only come from the ammonium ion. And only one of these actually contains ammonium, therefore our answer must be the ammonium chloride. For question 10, again another chemical test from that inorganic topic. What test is used to show that sodium chloride contains chloride ions? Well, if we're looking at the A, damp litmus paper turns red, that tells us that we have an acidic gas. And sodium chloride is not acidic, it is neutral. If the damp blue litmus paper was bleached, that tells us that we have chlorine gas, not chloride ions that we are looking for. So that then leaves us with our silver nitrate, and we're either adding hydrochloric acid or nitric acid. Well, the hydrochloric would give us a false positive, because hydrochloric acid, of course, already contains the chloride ions. Therefore, our answer must be D, where we have the dilute nitric acid being added to the silver nitrate, and we know for chloride it gives a white precipitate. If it was a bromide, we would get a cream precipitate, and if it was an iodide, we would get a yellow precipitate. For question 11, we're now looking at flame tests and again chemical tests. So compound X gives a red flame test. So that's either going to be a lithium ion or a strontium ion. And it gives a white precipitate on addition of dilute hydrochloric acid, followed by the barium chloride. And the barium chloride test is testing for sulfates. Which one is compound X? So we are looking for that mixture of either lithium sulfate or strontium sulfate, and our only answer therefore could be B. If it was calcium, it would give us not the red flame colour, and the chloride we would need to be using the silver nitrate test, and although the strontium would give us the red flame test, it wouldn't give us the white precipitate with the barium chloride. So our answer has to be lithium sulfate. Question 12 is looking at how we get the colours in a flame test. So the process of which this happens, well, we can automatically get rid of A and B, given the fact that they are talking about absorption of the visible light. It is not to do with absorption. That is something that will come into play later when you talk about transition metals. We know that it must be the emission of light or as a photon. And we have to look at, well, what's happening, and it's all to do with the electrons being excited and then undergoing de-excitation, or them falling back to lower energy levels. Therefore, our answer must be C. Question 13 is looking at the disproportionation reaction of chlorine with the hot concentrated potassium hydroxide. That's very important that it's hot, because we do get different substances. These are equations that you are expected to know the difference between. So we're going to have our potassium hydroxide, which is of course aqueous, reacting with the chlorine, which is a gas. And when it is in hot concentrated potassium hydroxide, we're going to make KCl, which is aqueous, plus KClO3, which is also aqueous, plus our water. And if it was cold, we would be making KCl plus KClO. Okay, so we're getting a difference in those substances there. And then we have to look at the oxidation numbers. So we know that our oxidation number of the chlorine is 0. When it is in KCl, well, the K is +1, so the Cl must be -1. So we're going to then get rid of D, because it can't be a +1. And then when it's in the KClO3, the K is +1. The oxygen is -2, but I have 3 of them, which gives me -6. And therefore, in order to balance it out, my chlorine must be +5. So my answer has to be B, -1 and +5. Question 14 is looking at the reactions of the halides with your sulfuric acid and what gaseous products are formed other than water vapour. And this is when we add the concentrated sulfuric acid to potassium bromide. So we have to think about what we're actually getting here. So we have the KBr plus H2SO4, and that's going to give us our KHSO4 plus our HBr. And then from the HBr, that is then going to react further, and we end up with the bromide ions forming bromine plus 2 electrons, and then the hydrogen ions from the HBr reacting with the sulfuric acid plus the 2 electrons, and that is going to give us water plus sulfur dioxide. So we're going to get Br2, hydrogen bromide, and sulfur dioxide being formed, and that would give us C. Our hydrogen sulfide, or our H2S, is only when we've got iodide. And because we have bromide here, of course, we're not going to form that. Question 15 is now looking at energetics. This is a topic 6 question. So we have the zinc reacting with copper 2 sulfate, and we're given the equation, and we are already given a delta H of -210 kilojoules per mole. This is telling us, of course, then it is an exothermic reaction. So we want to calculate the temperature rise in degrees when excess zinc powder is added to 50 centimetres cubed of copper sulfate containing 0.25 moles of copper 2 ions. So we have to think about the 2 equations that we're going to use. Now, normally we would start with Q is Cm delta T, and then delta H is Q over N. But we obviously want to work backwards to the delta T. So we're going to start by calculating Q, which is going to be delta H times N. So our delta H here is in kilojoules. I must change it to joules, so that becomes 210,000 multiplied by the number of moles of my copper, which is 0.0025. So my Q value is 525 joules. Now that I know that, I can rearrange my equation to find delta T. So delta T is going to be equal to the Q value over C times M, where C is the specific heat capacity and M is the 50 centimetres cubed. So we have 525 over 4.2 times 50. Remember, I don't need to change it into decimeters cubed. I keep it in centimetres cubed, and that is going to give me an answer of 2.5 degrees Celsius, meaning my answer is A. Just be aware, if you scale up your 210 kilojoules per mole incorrectly and you don't multiply it by 1,000, if you make a mistake and multiply by 100, you would get an answer of 25. So just be very careful when you are doing your scaling and changing your units, because sometimes you can get an answer that is one of the options, but it's not necessarily the correct one. Part B is then looking at what is this reaction. So the zinc with the copper 2 sulfate, well, if we look at what's happening here, essentially the zinc and the copper are changing places. Now, that means it's not a disproportionation because I don't have that change in oxidation number both for oxidation and reduction of one species. It's not a neutralization because there are no acids and bases here. And it's not a thermal decomposition because I'm not breaking anything down. That means my answer must be a redox reaction. And what's actually happening is we've got zinc solid reacting with copper 2, and we're forming zinc 2 plus copper solid. So we're getting oxidation and reduction happening, so therefore this is a redox reaction. And question 16 is looking at magnesium metal reacting with hydrochloric acid and what change would have no effect on the initial rate of reaction. Well, the most important thing to change any initial rate of reaction is we need to think about how we can get more frequent, successful collisions. Those should be the 4 most important words that you use in any rates of reaction question, because that is the key thing that you're trying to increase. You want more frequent successful collisions. So you want your collisions to be hitting each other, or your particles to be hitting at an energy over the activation energy. You want this to be happening as much as possible in the shortest amount of time. That is what rate is, because that will give you more product in a shorter amount of time. And all 3 of B, C, and D all give you more frequent successful collisions. The only thing that does not is changing the volume. Temperature, surface area, and concentration are all factors that affect the rate of reaction. So our answer here must be A. Question 17 is now looking at the Maxwell-Boltzmann distribution. So this is into our kinetics and equilibrium topic. And we have a Maxwell-Boltzmann distribution curve here, and we've got 2 sections of it. We have A and B, and we have our activation energy labelled. Now we want to look at, for part A, how does the peak change when the temperature of the reaction mixture is decreased? Well, what we need to understand is, what does a Maxwell-Boltzmann distribution tell us? And the whole point is looking at the temperature. So if we have a higher temperature, what that means is that we have a wider spread of energy. And that means that we've got our energy being spread out in more different ways across all of our particles. And what that does when we have a higher temperature is we have a wider and a lower peak. So our Maxwell-Boltzmann shape is the same, it's just wider, and our peak is at a lower amount. So actually what happens when we decrease the temperature is we get the peak getting taller like that and shifting more towards the left. Therefore, our answer must be A. Part B is referring to the activation energy. So the activation energy of the uncatalyzed reaction is represented as EA on the horizontal axis, and your A and B are your 2 areas on either side. We want to look at how do these areas change, if at all, when a catalyst is added. So if I go back up to the diagram, when we add a catalyst, what that does is it lowers our activation energy. So if this is EA of our catalyzed reaction. And what you can see is now all of this section becomes part of B. So our B section is getting wider, or is increasing, because we have more particles with an energy greater than the activation energy. And if B is increasing, that must mean that A is decreasing. Therefore, our answer is B. And our last question, question 18, looking at equilibrium. In an equilibrium reaction shown in our equation here, so we have 2NO2 giving you N2O4, a classic equilibrium question. They love to use this as an example. And at equilibrium, which of the following statements is not true? Well, before we even look at the statements, we have to think about, well, what is equilibrium? When we have dynamic equilibrium, we have the rate of the forward reaction being equal to the rate of the reverse. We also have our concentrations of our reactants and products are constant. Remember, they don't have to be equal, but they must be constant. And because we have our rate of our forward equaling our rate of reverse, that must mean that we have both the forward reaction and the reverse reaction happening at the same time. So that's the key parts of dynamic equilibrium. That's before I've even looked at the options. So now I can see A, the concentrations of the NO2 and the N2O4 are constant. Well, we just said that, so we know that that one's correct. The total number of moles is constant. Well, at equilibrium, we've got the concentrations being constant, therefore our number of moles must be constant. For C, the forward and reverse reactions have both stopped. Well, we know that that is false because we've just said that they're always happening. So our answer is going to be C, but let's just double check that D is the most key point of our equilibrium, that the rate of the forward reaction is equal to the rate of the reverse. And that is definitely a true statement. Now that's 20 marks of the 80 mark sample paper for Unit 2. It's very important for any multiple choice, as you've seen when we went through these examples, that you look at process of elimination. Look at the information that you're given in the question and break it down. Underline key parts, write key words next to it, anything that's going to help you then be able to get rid of some of your answers. And that makes your decision making of what is the correct answer that little bit easier. Check back on the playlist to see the written questions for this paper. If you've got any questions about the multiple choice, please feel free to leave a comment below.